we're doing cubic functions now. So we're doing everything we did yesterday, which was review, and we're going to apply it to more complex things. So to review yesterday, we had something called a 0 degree. And what does degree mean? Highest exponent, yeah. So if something's degree 0, that means the highest exponent is 0. So degree means highest exponent. This is called a constant. So if something didn't have an exponent, it would look something like this. Y equals 3. That thing has no variables, so it has no exponents. So it's degree 0. If you had degree 1, that means that you have something that is linear. Linear is something like y equals 2x plus 2, or y equals x. Right? The highest exponents on those things are the number 1. If something's degree 2, we call that quadratic. Quadratic often looks something like this, but it could also just be reordered all crazy if you wanted. You could do something like, and that would still be a quadratic because the highest exponent is only a 2. That is all grade 11. This is grade 12. So if something is degree 3, we call it cubic.
Doesn't it make a circle?
It won't make a circle. We'll graph a few and make some crazy things. Exactly, they look kind of cool. So examples of this would be something like y equals x cubed plus x squared plus x plus 1. That would be a cubic function, because the highest exponent it has is a 3.
Is there a go higher?
Yeah, we don't go higher. We do something else, though. That's another example right there. So I don't have to have an x squared term. As long as the highest exponent is an x cubed, it's still cubic. Okay, so I could get rid of the other terms and it's still fine. Yes?
You just have y equals x cubed.
Definitely. You could have y equals 2x. And that thing would be a cubic function. So as long as it's degree 3, you're going to have a cubic function. That's what makes this different. So, we're going to graph one. And we're going to see if we can do all the things we did yesterday, but now with cubics. So, we're going to graph this in our calculators, 2x cubed, 2x cubed. If you don't remember where your exponent button is to do cubed, use the little arrow, so it's above the division symbol. So 2x cubed and then it's plus 4x squared minus 3x plus 1. You might want to set your window to the same window that's already on this question. So your x minimum would be -3. Your x maximum would be 1. So if you want to graph your thing so it matches the graph that you're going to be drawing on, that's never a bad idea. So your x minimum is -3, x max +1, and then it goes -10 to -10. Or, sorry, -10 to +10. If you do that, and you use the window they have, you should end up with a graph that looks kind of like this. Looks a little crazy. If you zoom out and you look, you'll notice that this tail goes forever that way, and this tail goes forever that way. So by zooming out, you can see that that would happen. It just keeps going forever in a straight line after it does those crazy turns. All right, we're going to try to fill out this chart. So, the degree of this function. What's the degree of this function? 3. Highest exponent is 3, so the degree is 3. How many x-intercepts does it have? In this case, it only has one x-intercept. What's the y-intercept on this thing? It's 1. How do you know it's exactly 1? It's the constant. It's right there. Yeah, it's the end value. It's the last thing there. The constant is the y-intercept. Remember that. So the thing without any letters attached to it, once it's in general form, so it's all been multiplied. What's the end behavior? What does end behavior mean again? Where it's starting, where it's going. So what quadrant did we start in? We started in 3. And we went to 1. Remember labeling your quadrants. You start up here and you go counterclockwise. I always forget how to do it for. What's the domain? What's domain mean? Yeah, where the x values can be. So what's the lowest x value means? What's the furthest left that you could go? We could go forever to the left. What's the highest we could go? We could go forever to the right. So that means we just have x as the element of the reals. X can be anything. There's no restriction on it. What does range mean? Range is the y values, yeah. That means how low can it go and how high can it go. With these cubic functions, sometimes you get one like this, which can go forever down. And if you go to the right tail, it goes forever up. So that means y is the number for the reals. And the last question we have here is, what's the number of turning points? This thing would have 2 turning points. Remember, we're talking about changing directions. So this thing came up here. That would be a turning point where it changed and now it started going downhill. This is another turning point where it's changed and it's now going uphill. So the number of turning points on this thing would be 2. Yeah.
How do we know it will like change direction like way up higher in the graph?
You could keep expanding your graph to look at it. So like you could always make your window bigger, bigger, and bigger and see. The best way to know is to realize that it's just doing a steady pattern for a long time. Like it's just going in one straight direction. Or if you wanted to test it, what you can do is you can keep putting in numbers and see that it will start following a pattern of that it's only ever increasing. If you were to put in numbers and you were anywhere in this range, you would notice the numbers would grow a little bit less until they started all of a sudden not growing anymore. And then you would start growing it again and then not growing it again. If you put in numbers like -10 and then -11, -12, they would be growing by the same, basically, percentage. It would just keep getting bigger and bigger and bigger. All right, the other thing that we want to talk about now that we've seen a cubic function, we're going to stay on that graph for a second. I just want to see it. Oh, no, we don't. Okay. These turning points. We talked a little bit about it yesterday. How I said that the turning point is a vertex when we're talking about our quadratics. Well, now we don't really have a vertex because this thing could go up forever and it could go down forever. But you do see that there's this. There is a vertex if you look just in this area of the graph. That's what we call a relative vertex or a relative maximum. So this thing has a relative maximum right there. And it also has a relative minimum right there. We talked about our calculators yesterday, and we talked about, okay, why do you need to show your calculator where you want to find the maximum? Why did you have to do the left bound? Why did you have to do the right bound? This is why you have to do a left bound and a right bound. Technically, this entire graph has no maximum. But if I wanted to find the relative maximum in this region of the graph, That's why it lets you do left-bound, right-bound. And if, just for fun, we tried to find this relative minimum. Yeah. Okay. We have another one here. I want you to give that one a try completely on your own. I'll fill it out. If you finish that one quickly, feel free to move on to the next one as well. So there's 2 there you can practice on. But we will do this one together. So I want to give you a shot on your own. I'll fill out the information on the board so you can check to see if you're right or wrong. And then we're going to go over how we got it. Okay. Here we have a cubic function. We graphed it. The sketch is not a beautiful sketch. It's never going to be a beautiful sketch. You're going to have to accept that. Nice job just asking about my pictures.
I just asked you about your drawing because Mr. Gunnigan actually watched his parents just asked me about my earlier this semester and then just walked it. Showed up, sassed, left.
Yeah.
Just watching some
it's kind of neat.
Kind of creepy. But.
Alright, the other thing with this cubic is I'm going to put arrows on it. So remember that those arrows just tell you that the function is going to continue on in that direction with those exact same characteristics of like, I'm just going downhill this way forever. It's not going to do any more crazy turns or anything crazy like that. Alright, the degree of the function. How do you figure out the degree of the function easily? Highest exponent. So it's 3. So you just look for the highest exponent, boom, there you go. Number of x-intercepts. This one's a little tricky because it actually comes down and touches one time right there. It's hard to tell, but it does. And how could you figure it out? You could put it into your calculator, go second trace zeros, and see if it actually finds it on there or not. That's one good strategy. Another good strategy would be to actually try to solve that thing. Good luck with that. It's going to be a lot harder than it is easy. But your calculator will pick up on it if you go second trace zeros. If you have trust issues and you want to really see if it touches there or not, Ms. Shaw says she does, you could also even zoom in on that area of the graph to see if you can find if it touches or doesn't touch. And you can get close enough that you'll be able to see if it's down there or not. Okay? The y-intercept. How can we easily find the y-intercept? It's in the equation. It's the constant term. Good terminology, Jaden. Notice that I'm not writing just 36. I'm writing 0, 36. That's just a good habit to be in. So put it as a point. Remember, all y-intercepts have an x value of 0. The end behavior. Where does it start? Where is it headed? It starts in quadrant 3. As you move left to right, it's heading up into quadrant 1. The domain on this thing is just going to be x is known with the real, so it goes forever to the left, forever to the right. The range on this thing is going to be y-ER because it goes forever down and forever up. The number of turning points. So again, you want to check to see how many times does this thing go from increasing to decreasing or decreasing to increasing. So one time up here, we're going up, 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 and now we're going down. We come down all the way down here, and then all of a sudden we're going up again. So we have 2 turning points. Yeah. Good question. So we were doing that yesterday because our graphs look something like this. There's only one turning point. And more importantly, when we look at the range, it would say, well, I can go forever down, but I can't go forever up. There was a cap on this graph. On these cubic functions, there was no cap on it, so it could go forever to the up. There's a relative cap in this area, and a relative one in this area, but overall in this graph, I could go anywhere. I can go up forever or down forever. That's why we don't need to worry about finding the maxims or minimums yet. You could find the relative maximum and the relative minimum using the same trick as yesterday. All right, so we've got one more for good measure. So do your best to glide through this one. So again, you're going to do it on your own, and we're going to see if we can't draw any conclusions from looking at these things. So go ahead, graph it on your own, see what you come up with. You might want to try again setting up your y scale to be the same as theirs, so it's going up by 10. and down by 10, it just makes your graph look a little bit cleaner, and it looks a little bit more like theirs. If you're doing x scale, y scale of 1, you're not going to be wrong. It just doesn't look the same. Like, it doesn't look graphically as nice. That's all. This cubic function. So you're going to notice that the cubic functions all have the same degree. What's that degree?
3.
3. It's the highest exponent, right? It is a cubic function because it's degree 3. Anything higher than that, we're not going to look at degree 4, degree 5, degree 6, like you could go. They just add a lot more craziness. Well, you could look at it for fun if you wanted, but we don't get into it. We do get into another type of graph, but it's not to do with exponents like this. We get into a couple different graphs. Yeah, Jake?
For context, or we don't have questions like this, like charts.
It's possible, yeah.
Yeah, so how would the marks be for like the entire chart? Is it 1 mark or something? Or
I'd probably do a half mark per thing. Right, so if this was a test question, I'd probably go like half mark, half mark, half mark, half mark, half mark, half mark, like that. Probably wouldn't ask a number of turning points. Okay, so the degree of the function is always the highest exponent, which is 3. The next question is the number of x-intercepts. We have a different answer this time other than the other 2 questions. We have 3 x-intercepts this time. So that does change a little bit. And it does cross one more time over here. My graph, I drew the arrow too early, but you can clearly see it that it does cross again on your calculator. The y-intercept is at 0, -10. If you just put -10, that's no big deal. That's fine. The y-intercept does equal -10, so that works. The end behavior is different on this one. So the end behavior on this one goes from 2 to 4. So that one is also different. The domain and the range are still the same. Go forever left, forever right. The range goes forever down, forever up. And the number of turning points is still the same. There's 2 turning points. Yeah.
In a word question, would it ever get you to graph something like that, but don't only ask you about like a certain thing, and then you'd have to write y equals?
Correct. Yeah.
That's
So that's where this is headed. Is like tomorrow we're going to do more of these. We're actually going to create them out of raw data, and then we're going to use them to answer word problems. So for instance, if this was like, I don't know, the volume of a cube. It was like, what's the highest volume that you could have? Well, I'm not going to have negative sign length, so this would all be useless information. And then that's when that relative maximum becomes useful all of a sudden, because this data is not going to make sense in terms of the question. So that's how those relative minimums and maximums do come into play. All right. We have 6 graphs here, 6 questions. And we're going to try to match them up with each other. Before we do that, we're going to think about some things that we've seen. If we go all the way back to our quadratic, so I'm going to skip the pages way back to our quadratics. You don't have to, but I'm going to. If you graph these 2 quadratics, you notice that this one did this, and this one did that. And you should have known that from your Math 20 course. How would have I known that this graph was going to open up and this graph was going to open down?
the negative a value.
It has to do with, what we call the a value. So on a quadratic, the a value affects whether it's going up or whether it's going down. Another word for the a value is the leading coefficient. So it's the number that's in front of the highest degree, or the highest exponent. So in a quadratic, that tells me if I open up or if I open down. If we go back and we look at linears, you still have leading coefficients. And those leading coefficients tell you if you're going to have a graph that goes down, or if you're going to have a graph that goes up. And that's from Math 10. So Math 10, your leading coefficient told you down or up. Math 20, your leading coefficient told you if it was going to open down or open up. So in Math 30, what do you think, by comparing our graphs, we could maybe figure out what our leading coefficient's doing? So here, we have a leading coefficient that's positive. On our next slide, we have a leading coefficient that's positive. And here we have a leading coefficient that is now negative. And if you look at the shapes of the graph, the two that are positive both follow the same kind of path. They started in 3, they went up, they curved, and they ended in 1. Same thing. Started in 3, went up, ended in 1. Change the leading coefficient, and it's like the graph flips upside down. Now it goes down, up, down, and ends up going down into number 4. So your leading coefficient for cubics tells you what your end behavior is going to be. If I have a negative leading coefficient, I'm going to go from 2 to 4. I'm eventually going to work my way downwards. If I have a positive coefficient, I'm eventually going to work my way upwards. So eventually I'm going to go from left to right and go up. So if I look at these graphs, I can use those tricks. So my Math 10C trick, and my Math 3-1 trick, and my Math 3-2 trick, to figure some of these out really quickly. Like for instance, I have 2 cubic graphs. I have graph number 4 and graph number 6 are both cubics. This one goes from 3 to 1. So eventually it works its way upwards. That means it has a positive leading coefficient. This one worked its way from 2 down to 4. So it went downwards overall, meaning it has a negative leading coefficient. So the leading coefficient on a cubic can help you identify graphs really quickly, and if you've done them right. I know that this one has to have a leading coefficient, so these have to be the matches. That's the only cubic that has a leading positive coefficient. So number 5 is going to be IB. Number 1, I can't circle. Number 1 has a negative leading coefficient, so it has to eventually be working its way downwards, which would be BI. Yep.
Why is number 5 IB?
Why is number 5? I'm sorry. Why is number 5 IB? Not number 4? Oh, number 4 is quadratic, not a cubic. Yeah. For a second there, I was like, oh crap, there's another quadratic or cubic there. All right, what other tricks do we know? So, what do we know the constant term tells us? Constant term always tells us our y-intercept. So that's another way that we could easily figure things out. If I look at my 2 quadratics, this one's got a -2 constant. This one's got a +1 constant. So that helps you divvy up those ones. Graph 5 has to have a +1 constant, and it has to be a quadratic. That would be this. So number 4 is D. So you can use these little tricks to quickly figure things out rather than having to graph all of them, match your window to all of them. That would take a long time. This quadratic had a constant of -2. Constant of -2 is number 3. So number 3 is double R. Now you're down to 2 lines. They both have to have negative leading coefficients because they both work their way down as you go left to right. This guy has to have a constant, a constant of -3. This guy has to have a constant of about -3. So neither of those tricks are going to work. What else do we know about linear equations?
The smaller the number of x is the smaller the number in front of the x,
the flatter the line's going to be. So the higher the number, the steeper it's going to be. So that's right, that's our slope trick. So in a linear equation, you can figure out your slope by looking at the number in front of the x. This one is going to be flatter than this one because it's got a lower, this one's got a lower number. Yep.
On the diploma, do we have like a section that you were not allowed to use a calculator?
No, you'll always be allowed to use a calculator. So if you had to, you could graph all 6 of those things and do that. I don't think you get a question this nice on the diploma. That'd be pretty nice. Yeah. More or less, we're trying to see some trends in things, like things we know now. We know our leading coefficient guides the way things look. We know our constant tells us where things are. And we know our slope can tell us if we're flat or if we're steep. Which one is flatter? So I is going to be the steeper one, and triple I is going to be the flatter. All right. Some recap. So we're going to do some notes here. So bear with me. How are the domain and the range of a polynomial function related to its degree? So if we think about our degrees, when we did domain and range on those really early ones, those straight lines, the domain was always XER. When we did the domain for our quadratics, it was always XER. When we did our domain for our cubics, it was always XER. So the domain is always going to be XER, no matter what the degree is. And I'm going to pull out a little thing that has nice notes in a second if you want to copy exactly what it says. The range. When I had degree 1, so you don't want to write down what I'm writing. Degree 1. The range was going to be what? YER. That was just a straight line. It went up or down. We did that. If it was degree 2, that's when we had a minimum or a maximum. These caused quadratics. So degree 2 had to be y is greater than or y is less than something. When we did degree 3, our cubics from today, we looked and we noticed that every single one was YER again. That's not a coincidence that degree 1 was fine, even degree wasn't, odd degree was good again. The notes that you want to copy, if you have an odd degree, you're always going to be YER. Because it's always going to go from either increasing to decreasing overall, or from decreasing to increasing overall. If you have an odd degree, or an even degree, it's always going to end up going really high and then really high again, or really low to really low again. So an even degree range is dependent on the absolute minimum or absolute maximum value points. So you're going to have to find some mins and maxes to figure out your range with the degrees. Hey. Yeah. So our second question says, how is the number of turning points of a graph related to the degree of a polynomial function? This is what affects your range. The most number of turning points you're ever going to have is one less than the degree. So if you think about what we've seen degree 1. Degree 1 always looked like a straight line. Degree 2 always had one curve. Degree 3 to this point has always had two curves in it like that. That is not a coincidence. So the most number of turning points you could ever have is one less than the degree of the function. It doesn't mean that is the number that you're going to have. That's the maximum number of turning points you could have. You'll never have more than the degree. We'll talk more about turning points a bit. So the maximum number of turning points is one less than the degree of the function. How is the end behavior of the polynomial function affected by the degree? Well, the end behavior is obviously going to be affected by the number of different turns you're going to do. Because that determined if I was going up or down by the end of how many turns I did. So, even degrees will have similar end behavior, and odd degrees will also have similar behavior if they have the same coefficient sign. That's the leading coefficient. Remember how we talked about positive leading coefficients versus negative leading coefficients and what they're doing? That's what this is talking about. So if two things have a positive coefficient, they will have the same end behavior. If two things have negative, they will have the same end behavior. All right, x-intercepts. If you look back at all the graphs we did, you'll notice, and I think it was, I want to say Hannah who noticed it, said there's always two x-intercepts with our quadratics. And when we're doing straight lines, she's like, there's always only one x-intercept. Well, that's the same number as the degree. However, that's not a guarantee, and that was my response yesterday, was just because you have degree 2 doesn't mean you'll have two x-intercepts. What it does is it means you'll have at most two x-intercepts. So the maximum number of x-intercepts that a graph may have is equal to the degree of the polynomial. So if I have a cubic function, the most x-intercepts I can have is 3. I'll never have 4. But it could be lower than 3. I could have 2, could have 1, could have 0. Same with a quadratic. We did see examples of quadratics that had no x-intercepts. It just ended up where that quadratic was, it never did touch it. Oh, computer just got stuck. Why and how does the sign of the leading coefficient affect the end behavior of the graph of each type of polynomial function? Again, talk about this a little bit. However, this will break it down nicely for you. So you have a nice little chart there. The chart's what's important. You don't need to write out all the words. That's just keeping what's in the chart. So if you have a linear function and you have a positive coefficient, you're going from 3 to 4. Sorry, 3 to 1. If you have a negative coefficient, then you'd be going from 2 to 4. Again, that's the difference between going up or down. Yeah. Bigger? Good job. Bigger. It did it. Does that help? Okay. So if we were to picture these things, you draw a graph for each one of them. This is your end behavior, depending on if your leading coefficient is positive or negative. So if I'm positive, I'm going uphill. If I'm negative, I'm going downhill. For a quadratic function, if I'm positive, it means I'm opening up. So I go from 2 to 1. If I'm negative, I'm opening down, which means I'm going from 3 to 4. For cubics, if it's positive, that means I start low, go up, then down, and up. So I go from 3 to 1. And if I'm a negative leading coefficient, it's just flipped upside down. So it's going down, then up, then down. That's obviously not what it's always going to look like, but in general, that is what it'll look like. It'll go from that quadrant to that quadrant every time. Okay. How many y-intercepts do polynomial functions of degree 1, 2, or 3 have? How many y-intercepts have we always had? Just one. And why did we only ever have one? Because it was equal to the constant term. You can only ever have one constant term. The reason why. So let's imagine I have a function. When it has two constant terms. I would never leave this written as 2 plus 4. Instead, I would make it plus 6.
Would the calculator automatically figure that out?
Yeah, it would know. It would do it for you. So if you can only ever have one constant, then you can only ever have one y-intercept. So no matter the type of thing we have, there will only be one y-intercept, because you can only ever have one constant. The thing that sometimes will throw people off is they'll see something like this, and they'll say there is no constant. That means there is no y-intercept. But if there is no constant, it's like adding 0. We just would never write plus 0. So this would have a constant of 0, meaning the y-intercept would be at 0. Why do, oh, you can't see it. Why do some cubic polynomial functions have turning points but not maximum or minimum values? And we've talked about this as well. So we've talked about the fact that, oh, we haven't seen a graph yet of this. We're going to see a graph of this. When you do quadratics or cubics, sometimes what you're going to get, you're going to get graphs that look like this. They're going to go up, and then they're going to wiggle a little bit like that. And they're not actually going to have a full maximum or minimum. They're going to have something called like a flat point. We will talk more about those when they come. It's just how those graphs work out. It has to do with the way that they can factor out and stuff like that. So for now, all you need to know is that if you have a flat spot, it's called a point of inflection. It's not a maximum or a minimum. If you look at it, it looks like there's no minimum or maximum. You should be able to tell it just goes up, goes flat, and then keeps going up. So it wasn't a maximum point because it could have kept going up. It wasn't a minimum point because if you went to the left, it kept going down. So flat spots don't have max or min. That's all you really need to know. They're called points of inflection. How is the constant term in general form of any polynomial related to the y-intercept of the function? We've said this 2 million times. The y-intercept is the constant. If you just write y-intercept is the constant, that'll be a perfect thing to write down. That's all you need to know. So the y-intercept is the constant. How can you predict the characteristics of a graph given its equation? Well, this is what we talked about a little bit ago again. And this is just all review and recap. We can predict by looking at the leading coefficient. We can predict by looking at the constant term, right? And we can predict by looking at the degree. So by knowing those three things, just by looking at a function, we should be able to figure out a few things about every single graph. This has it all written in there. Again, if you don't want to write it all out, that's fine. The three things you need to know: the constant tells you the y-intercept, the degree tells you the shape, and the leading coefficient tells you the direction. That's the three big things, and we've talked about it a few times. It's just good to have it written down somewhere to reference.
What was that sentence?
The last one was that the leading coefficient tells me the end behavior, where it starts and where it ends. Those are the three things that when we look at any graph, we can look at it and kind of predict how it looks. We can't be perfect, right? I'm not going to know where every single minimum and maximum is just by looking at it, but I'll know that there's going to be maybe 2 minimums and maximums, or something like that.
What's the degree one?
The degree tells you the shape.
The degree tells you the shape, right? Degree 1 is going to be a straight line. Degree 2 will have one curve. Degree 3 will do that little wiggly thing. Good review question. A little bit of math 10C in here for question 10. How can you tell if a graph is a function? Yeah, the straight line test or the vertical line test, same thing. So if you take any graph and you run a straight line across it. If that straight line crosses that graph more than once, then it's not a function. So we call that the vertical line test. So we say if it passes the VLT. Again, you're really not going to be tested with vertical line test. You might, but we can talk about if you're confused on it. And that is a perfect place to stop. There is a little graph here that kind of highlights everything that we now know about all 4 polynomials.